Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 3 of my course on experimental model analysis. In the previous lecture we studied lump parameter models. Lump parameter models are nothing but collection of discrete masses, springs and dampers. And in the last lecture we saw that how these models are obtained with an example of a automobile. So in this lecture we are going to study that how to obtain corresponding mathematical models for these lump parameter models. So lump parameter models can be looked upon as physical models of the system, and then how we obtain corresponding mathematical model of the system is something we are going to study in the lecture today. Also we would like to study that how we obtain the dynamic response of the system using the mathematical equations we obtain. Specifically we are going to talk about analytical model analysis of single degree of freedom undamped systems today, and then we are going to see that what are the free and force vibrations of single degree of freedom undamped systems. So therefore our topic today is analytical model analysis of single degree of freedom and damped systems. And under this we are going to study the free and force vibrations of these systems, right. So before we start talking about free vibration, let us first define, or let us try to understand what is the meaning of these terms single degree of freedom system and multi degree of freedom systems. So what do you mean by single degree of freedom system? So as far as the terminology degree of freedom is concerned, we have talked about this in the previous lectures, which basically says that the number of independent physical coordinates which are required to specify the displaced configuration of a system, that is nothing but the degree of freedom. But then what do we mean by single degree of freedom system? So in practice we see that all systems are continuous, right. They have a continuous distribution of mass, stiffness and damping. So and hence they have infinite number of degrees of freedom, okay. So that way we cannot refer them as either single degree or multi degree of freedom system with finite degrees of freedom, okay. So then what is mean by single degree of freedom system or say multi degree of freedom system? Let us take the example we discussed in the previous lecture, the car moving on a rough road, and we saw that to study the bouncing motion of the car we could construct a single degree of freedom model to study the bouncing motion, okay. And if that is the objective, then the single degree of freedom model probably would be adequate to study the bouncing motion, right. And therefore the single degree of freedom system therefore can be referred or refers to a physical system whose dynamics can be approximated by a single degree of freedom model for the objective under hand, right, or the objective for which the model has been met, right. So single degree of freedom system refers to a physical system whose dynamics can be approximated by a single degree of freedom model for the objective of the study, right. So, we also saw that if the objective was in the car example to predict the bouncing motion as well as pitching motion, then the single degree of freedom model was not good enough, right. So, we made another model. So, that is why the approximation by single degree of freedom model would be based on the objective, that is what is the intention of the study, what is the objective of the study. Similarly, a multi degree of freedom system right, it refers to a physical system whose dynamics can be approximated by a multi degree of freedom model, right, for the objective of the study. So, if modeling the dynamics of a physical system which is actually continuous, if that can be represented by a multi degree of freedom model, then we may refer for the purpose of that objective the physical system as a multi degree of freedom system, right. So, in practice all systems are continuous, and strictly speaking none of them are either single degree or multi degree of freedom systems with finite degrees of freedom, right. But for the certain objectives of the studies we can approximate them as single degree or multi degree of freedom models, and such systems therefore we can refer as for those objectives we can refer them as single degree or multi degree of freedom systems. So, let us now talk about free vibration, right, of single degree of freedom undamped systems. So, I think we need to define two terms here, right. First is what is free vibration. So, free vibration refers to vibration of the system when no external forces are continuously acting on the system, okay, and the vibration occurs because of any initial disturbance given to the system, right. So, if we give some initial displacement or velocity, or we apply some impulse on the system, then system vibrates, right. So, because such vibrations are referred as free vibration. But if a system is being continuously acted upon by some external force, right. Let us say in the case of car example, if the engine is on, right, if the car is moving, engine is on, and because of the forces generated by the engine and because of the excitations from the ground, right, the car body would be continuously excited. So, those vibrations would be nothing but force vibrations, right. So, therefore, free vibration refers to vibration when, or rather we can say that free vibration due to initial disturbance, or excitation. The second term I think we need to define is what is undamped system. So, undamped system refers to a system with damping not being modeled, right, or if the system does not have damping. So, undamped system is a system with no damping. So, such systems with no damping can be conceived in a theoretical manner, right. So, theoretical systems we can have as systems without damping, okay. So, we can have a collection of, for example, discrete masses and springs, and that system would be an undamped system, right. But in practice always all systems will have some mechanisms through which the system dissipates the energy of the system, and hence some amount of damping will always be present in practical systems. Some systems may have a higher level of damping, some systems may have a lower level of damping, but irrespective of the level of damping some energy dissipation would always occur, right. And therefore, in practice or in practical systems damping is always present and systems are never undamped systems. Okay. So, undamped system is an idealization of a practical system or representation of a system through an undamped model, right. That is basically an undamped system. So, obviously, the question arises, if damping cannot be neglected in practice, why one should be worrying about the analysis of undamped systems. The reason is that undamped systems or undamped models rather of practical systems can be used to predict the natural frequencies of the system, and natural frequencies affect the dynamic behavior of the system a great deal. Therefore, in the analysis of the practical systems the undamped characteristics play a role in determining their behavior, and hence the analysis of undamped system, or rather analysis of the practical systems through an undamped model also has its value. So, let us now see that how we can obtain a mathematical model for a given undamped system. So, let us first of all take an undamped system. So, let me choose an undamped system like the signal telegraph freedom model we got for the car in the previous lecture. This is the mass, then we have the spring representing the stiffness of the system, okay, with units Newton per meter and mass as units kg, right. And now our objective is to obtain a mathematical model, right, and this can be called as a physical model of the system. Right. So, this is nothing but the physical model of the system. For example, the car system, this is a physical model of that car system, right. And now we want to know what is want to obtain what is the corresponding mathematical equation or the model which represents this, or which defines or describes this physical model. So, now to obtain mathematical model we need to invoke the relevant physical law, right, which describes the the behavior of this system. And the physical laws, there are alternative physical laws which are all equivalent, but either of them can be used to obtain a corresponding mathematical model of this physical model. So, and those physical laws are, so we can use for example Newton's law, or we can use D'Alembert's principle, we can also use law of conservation of energy, which is referred as energy principle. We can use principle of virtual work, right. We can use Lagrange's equation, or we can also use Hamilton's principle. Okay. So, Newton's law and D'Alembert's principle, they are based on analysis of the forces, right, considering the equilibrium of the forces acting on the system, right, while the other four are basically based on energy aspects, right. So, in many complex systems, for example, or if the system is complex, often the application of the force based principles or becomes tedious, and hence in those cases, for example, Lagrange's equation or Hamilton's principle will be easier to apply. However, we are going to consider now the Newton's law to analyze this system. So, we are going to consider now the Newton's law, right, to obtain a mathematical model corresponding to the given system. So, therefore, if we consider now the static equilibrium, right. So, under the static equilibrium, so what is going to happen if the, let us say this is the undeformed system, right. If that is the undeformed state of the system, then what is going to happen? Because of the weight of the mass of the system would deform like this, right. And so, if this is the mean position, then this is nothing but the static deflection, right. So, delta is the static deflection, right. And so, for the under static equilibrium, right. So, for under static equilibrium, we can make the free body diagram of the mass. This is the free body diagram of the mass. So, the forces, so for to make the free body diagram, we need to show all the forces which are acting on the mass. So, one force is due to the spring. So, when the spring is compressed, so what is going to happen? The spring is going to apply a force in the upward direction, right, like this, which will be nothing but k into delta. And then there is the gravity force mg, right, and hence under the equilibrium we can say that k delta, right, should be equal to mg. So, now we consider the under the vibratory motion, what is going to happen, right. So, we need to now consider the dynamic equilibrium. So, under the dynamic equilibrium, what is going to happen is this mass, let us say now this is the, let us treat this as the reference position, right. This is nothing but the static equilibrium position, right, and let us treat this as the reference. So, we are going to measure the vibration or displacement due to vibration with respect to this static equilibrium position. So, when that happens, then let us suppose that the mass moves by distance x, right. So, let us say this is the displacement x of the mass, right. And now we need to make the free body diagram again in order to write the equilibrium under the displaced condition, right. So, under the displaced condition, if we make the free body diagram, then we will have the force, right, which is acting, let us say the force due to spring would be due to the net deflection. So, x minus delta is the net deflection of the spring, and hence the force would be k into x minus delta, assuming x is more than delta. And then we also have the gravity force, and plus this mass has acceleration x double dot. So, the notation we are going to use here is that if, so the notation, so derivative of displacement with respect to time once, right, this would be represented as x dot, and derivative of time, derivative of x with respect to time twice would be represented as x double dot. So, each dot over x represents derivative with respect to time once, okay. And now let us apply Newton's law. So, by Newton's law, so the mass into acceleration should be equal to summation of all the forces which are acting on the mass, right. And in our case those forces are minus k x minus delta and minus mg, right. So, in the light of the static equilibrium condition, k delta is equal to mg. So, this mg and k delta would cancel out, and then we would be left with mx double dot is equal to minus kx, right, or mx double dot plus kx is equal to 0. So, this is basically the equation we are getting, right. So, this is nothing but said to be, this is said to be the equation of motion, okay. this is said to be the equation of motion of the single degree of freedom system. Okay. So, one thing we should now see here that the equation is nothing but mx double dot is equal to minus kx, and what does it represent? It represents simple harmonic motion. Okay, which basically means that simple harmonic motion, the acceleration is proportional to displacement, as is the case for this system, and it is in the opposite direction, right. Acceleration is opposite to that of the displacement. So, therefore, we see that the motion of this system, right, the free vibration motion is basically nothing but a simple harmonic motion, okay, because here these two conditions are satisfied. The acceleration is proportional to displacement and is negative of x, right. So, therefore, if we think of solution of this differential equation, right, so which is nothing but the differential equation we got is mx double dot plus kx equal to 0, right, and we note that this is a second order differential equation, it is a second order ordinary differential equation. Of course, it is linear because m and k are constants, and the power of x and its derivatives it is only the first power, first degree, and it is also a homogeneous equation. So, now the solution of this equation would be definitely a simple should represent a simple harmonic motion, and simple harmonic motions are represented by we can say one solution is a cos omega t, right. So, cos and sine functions they basically represent simple harmonic motions, and hence the solution is either a cos omega t, or we can also call it, say, other possibilities b sin omega t, right, where omega is the frequency of the simple harmonic motion, right. So, the coefficient of t refers to the frequency of motion, the coefficient of t it refers to the frequency of the motion or the simple harmonic motion. Okay. So, now to check whether this indeed is a solution or not, we can substitute this in the differential equation, right. So, if we substitute this in the differential equation, what do you get? If I differentiate cos omega t twice, I get minus a omega square cos omega t, right, plus k a cos omega t is equal to 0, right, and I get, sorry, I also have an m here which I have forgotten to write. So, k minus m omega square a cos omega t is equal to 0, right, that is what we get. So, in this case we see that a cos omega t obviously cannot be 0, because if that is 0, the displacement is x becomes 0, and then it would not represent the vibratory motion of the system, which actually is the reality, and hence a cos omega t cannot be 0. The only way this equation can be satisfied is when k minus m omega square is equal to 0, which means the omega square is equal to k by m, or omega is equal to square root of k by m. Okay. So, therefore, the interpretation of this is that x is equal to a cos omega t would indeed represent the solution of this differential equation, or the solution of the, or it would represent the motion of the vibratory system if the frequency omega of the motion is under root k by m, right. And because x is equal to because the system is vibrating freely, it is vibrating naturally without any forces exciting the system, okay. and hence that vibration is nothing but the natural vibration or free vibration, right. So, we have the free vibration as no external forces are acting, right, and hence this we also call as natural vibration. It is a natural vibration, and therefore, the frequency of this vibration, frequency of the vibration which is currently a simple harmonic motion is, or it is we can call that as the natural frequency, because the frequency of the natural motion or natural vibration, and therefore, the frequency omega can be appropriately referred as omega n, right. We can refer this as omega n, the natural frequency, right, and hence we say that omega n is equal to under root k by m for this single degree of freedom system. Okay. So, therefore, not only x is equal to a cos omega t would satisfy or satisfies this equation, but also b sin omega t would also satisfy this equation, and therefore, a general solution of the differential equation is given by a linear combination of these two distinct motions, right. So, we say x of t is equal to a cos omega t plus b sin omega t, and then let us also add subscript omega subscript n, because now we are calling it as natural frequency omega n. Now, here a and b are arbitrary constants, right, and they depend on initial conditions, on the motion of mass, right. Now, this system is a second order system, right, because the order of the differential in the equation of motion is 2, it is a second order system, and a second order system requires 2 variables to be specified to prescribe or describe its state of motion, right. So, it requires 2 variables to prescribe its state of motion, or it is the dynamic state of the system completely, right, and that is why in fact that is manifested in the form that in the solution there are 2 arbitrary constants. So, the fact that the system is a second order is manifested in the fact that there are 2 arbitrary constants in the solution. So, therefore, we require 2 variables to be specified, and generally the displacement and velocity are specified as the initial conditions. So, the state of the mass or state of the dynamic state of the mass is specified by specifying the initial conditions, right, on the displacement and velocities. So, let x naught be the initial displacement and v naught be the velocity. So, therefore, if we now we can formally write as at t is equal to 0, if we call the the initial time as t as 0, then at t is equal to 0 x of t is equal to x naught and x dot of t, right, which is the velocity, is v naught. Okay. So, now we can use these 2 conditions to find out a and b by substituting these conditions in the equation, right. So, if we do that so we can easily do that, say we can say that x naught is equal to a plus this is 1 then b into 0, right. So, this leads to a is equal to x naught. Similarly, we can differentiate the velocity, the displacement to obtain A omega n sin omega n t plus B omega n cos omega n t. And now if you impose the second condition, which is V naught is equal to this would be 0 at t is equal to 0, and this would be B omega n. So this leads to B is equal to V naught by omega n, right, and hence the solution due to the initial displacement and velocity can be written as x naught cos omega n t plus V naught by omega n sin omega n t. So this is nothing but a general solution of the system under free vibration, right. This is the general solution. And if you plot this, essentially how it is going to appear, it is going to look something like this, x t and something like this. So this motion will continue like this, okay. So therefore this is the time period of the motion, which is t, right. So the time elapsed between two corresponding points in a cycle, right, is basically so this is, you can see, if I treat this as the initial point, then this cycle is completed at this instant, right, and hence this is nothing but the time period, and this is nothing but equal to 2 pi upon omega n, okay, and this is nothing but the amplitude, this is nothing but the amplitude of the motion, okay. So therefore in the free vibration, one important characteristic is that the vibration occurs at the natural frequency. So under free vibration of a single degree of freedom system, the vibration occurs at the natural frequency of the system, which is nothing but under root k by m. Now we are going to talk about the force vibration. Right, and then specifically we are going to consider the harmonic force, harmonic excitation, right. We are going to consider harmonic excitation, which means that we will assume that let the force be of the form f of t is equal to f naught cos omega t, right, which means that the force is of this form. So it is a cosine wave like this of constant amplitude f as a function of time, right, and the amplitude of the force is f naught, okay, and therefore the system now, if I now make the, let us quickly make the system again. So this is the static equilibrium position, right, this is the static equilibrium position, okay, and then we have, this is the mass m, this is the stiffness k, and then we have a force f of t acting on the system. So now we again would like to invoke Newton's law to write equation of motion for the system. So by Newton's law, right. So again we need to now make the free body diagram of the mass. Let us do that. If this is the mass, so now we have the force f of t, and then we have the displacement. We have the force due to spring, which is k. Now question is here, should we take static displacement of the system into account? So from the free vibration analysis we learn that if we take the static deflection into account, then obviously we could also take the gravity force into account, and then in the final equation these two forces cancel out, right. So the gravity force does not appear in the final equation, right, as do the static deflection. So and that happens because at static equilibrium position the gravity force is balanced by the static deflection in the system. So we can make a simple thumb rule that in all the systems, in any given vibratory system, if the gravity forces cause static deformation of the system, then they would not appear in the final equations, right. But if the gravity force is not balanced or is not balanced by static deformation in the system, then the gravity force or gravity term would appear in the final equation. So one example of this is a simple pendulum. In the simple pendulum, we see that in the final equation the gravity term G appears, okay, and that in fact provides the force of restoration whenever the pendulum is disturbed from its static rest position, right. So that is why we see that in the pendulum system is the system where we see or we do see the appearance of G in the final equation. But in a spring mass system, the example we analyzed today, we do not see the G term appearing in the final equation simply because the gravity term or gravity force is balanced by the static deflection of the system. So in the present case also the same thing would happen, and hence it is no longer necessary for us to take into account the static deflection and the gravity force of the system into account, right. Hence we would simply assume that the mass is displaced let us say by a displacement x from the static equilibrium position like this, okay, and then we can simply write the force as kx, right, and then the mass as acceleration x double dot, okay. So if you now apply Newton's law, then what is going to happen? Mx double dot summation of forces acting on the mass. So f of t is in the direction of acceleration, so we take it that as positive. The spring force is opposing the acceleration, so we take kx, and that leads to mx double dot plus kx is equal to f of t. So this is the equation we got. So now we see that on the right hand side no longer it is 0 as we got in the free vibration case, right. It is a term non-zero term, and then it is not dependent or related to x, and hence the system is now a second order differential equation, of course ordinary differential equation. It is linear, but now it is inhomogeneous, right, it is inhomogeneous. So let us now see that how we can solve this equation. This being an inhomogeneous equation, the total solution, it consists of two parts. One is the complementary part, we are representing as xct, and a particular part we are representing it as xpt, right. So this complementary part is the, so if we determine first of all complementary part which is xct, right. Then this complementary part is nothing but the solution of the corresponding homogeneous equation. Complementary part is the solution of the corresponding homogeneous equation. And what is the homogeneous equation? We simply make f we consider f as 0, right. That is the corresponding homogeneous equation, and already we have got the solution of this equation, which was xct is equal to a cos omega nt, right, plus b sin omega nt, okay. So the complementary part of the general solution we have obtained. Particular part of the solution, now we find okay. So this particular part of the solution is nothing but the solution of the homogeneous equation, right, a particular solution of the homogeneous equation. In our case it was mx double dot plus kx equal to f of t, and f of t is harmonic force f naught cos omega t, and hence we have this equation. So a solution x of this equation is nothing but a particular solution, and when that is added to the complementary function, we get the complete general solution, right, or the complete solution, which is referred as general solution, and which represents all possible solutions or the system may have for any arbitrary initial conditions. Now here, because the forcing function is a function of frequency omega, so we expect that the system would respond with the same force. Its response is going to vary at the same rate, and hence it is logical to assume the particular solution as being of the same form, that is cos omega t, but with having an amplitude say xpo, right, or xp naught. So that is the amplitude of the particular solution. So now we can substitute this in the differential equation, because if that is the solution, it must satisfy the differential equation. So when we do that, what we get is this minus m omega square xp naught cos omega t plus k xp naught cos omega t is equal to f naught cos omega t. So cos omega t would cancel out from here, and what we get is xp naught is equal to f naught upon k minus m omega square. That is what we get. Okay. So this is nothing but the amplitude of the particular part of solution, and we can also write it in this form. If I divide the numerator and denominator by k, then I get m omega square by k, which I can also write as this. I can refer as x static, f naught by x, k is the static deflection, right, and here k by m can be written as omega n square, and hence this becomes omega upon omega n whole square, right. So here x static is the static deflection. So here we have used the symbol x st in the subscript, though in the previous case we called it as delta. So both are same, static deflection, which is equal to f naught by k. Okay. So either expression can be used to represent xpo, and therefore we get now the total solution. So this is the particular solution. Therefore the complete solution of the system is given by x of t is equal to a cos omega n t plus b sin omega n t plus now xpo, right, which we got as x static upon 1 minus omega upon omega n square cos omega t. So that is nothing but the complete solution of the differential equation. Before we talk about the nature of this solution, let me also present now an alternative method to find a particular solution, right, which we are going to refer as complex exponential method, right, and this is for to find particular solution. To harmonic forces. So if a force is harmonic, we can use this method to find a particular solution to a harmonic force. Okay. So the idea of the method is that instead of finding the response to the actual force, which is f naught cos omega t, we find response to a complex exponential force whose real part is the actual force f naught cos omega t. That is the idea. So therefore if we take the complex exponential force as, if I use an overbar to represent the complex exponential force corresponding to the actual force, then this is nothing but f naught e to the power I omega t, right, and we note that the actual force, which is f of t, right, is nothing but the real part of this complex exponential force, right. So the idea of the method is that we find response to f bar t, which is the complex exponential force, And then once we have found a response, which again we can refer as the complex response, then the real part of that complex response should then be the response to the actual force. Okay. So, that is what we expect. So, therefore, before we proceed further, let us also try to see what this complex exponential force is. So, I can show this on a complex plane, where I show the imaginary part of the force on the y axis and the real part of the force on the x axis. And now you can see this complex exponential force can be shown like a vector, right, f naught e to the power I omega t. And because t is continuously changing, it is like a rotating vector. So, this f bar t can be shown by a rotating vector. So, if the length of this vector is f naught, right, and if x axis is taken to represent time t is equal to 0, right, or rather time t is equal to 0 is assumed to coincide with the x axis, then this angle would be nothing but omega t, right, if this vector rotates with an angular velocity omega radians per second, right. So, if the vector rotates with omega radian per second, then this angle would be omega t. And now if I see this, if I take the real part of this, which is this one, right, this is the real part, okay, and this real part is nothing but, we can easily see this real part is f naught cos omega t, right. So, therefore, this vector is in the vector notation, this vector is nothing but f naught e to the power I omega t, right, because it consists of two parts, f naught cos omega t plus I f naught sin omega t, right. And the imaginary part of this vector, which is this one, this is the imaginary part, this is nothing but f naught sin omega t. So, if we combine the real and imaginary part, right, using complex notation, then we end up with f naught cos omega t plus I f naught sin omega t, which can be written using Euler's identity as f naught e to the power I omega t. So, therefore, complex exponential force is like a rotating vector in complex plane, right, it is a rotating vector in the complex plane, right. Then what we do now, we assume that, so our objective now would be to find the response of the system to this complex exponential force, that is f naught e to the power I omega t. And now we assume that let the particular part of the response, which we are going to now call as xp bar showing the complex response to the complex force, we can represent this as xpo bar, right, e to the power I omega t. So, this we are assuming to be the probable solution, right. Now, we need to substitute this in the equation of motion, and therefore, now we need to differentiate. So, to differentiate, let us so what we see is that xp bar dot, right, this is nothing but derivative of xp bar with respect to time, right, and because xp bar is nothing but xpo bar e to the power I omega t, what we get is nothing but I omega times xpo bar e to the power I omega t, right, and which is nothing but x I omega xp bar. So, this shows that if I differentiate a complex quantity, right, in the form of a complex exponential form, then differentiation is a simple process. We need to simply multiply the complex quantity by I omega, as we see from here. And if I want to now differentiate it twice, then I can repeat this process, and I would see that I need to again multiply this xp bar dot with I omega, right, that would basically give me minus omega square xp bar. So, that is in fact the advantage of this complex exponential method, that the differentiation can be carried out very easily. So, the mathematical process of finding the solution becomes easier. So, that is an advantage of the exponential method. Okay. If you want to integrate a complex exponential, you need to just divide it by I omega. So, that also is simple, and even if you want to take ratio or multiplication of two complex quantities, the process is very simple as compared to if the same processes are to be applied to trigonometric functions like differentiation, integration, all these processes, they are little bit mathematically more tedious when the trigonometric functions are involved, and hence this method offers that advantage of algebraic simplicity. And hence what we would do in our later lectures, wherever required we need to find the response, we will use the complex exponential method, right. And hence let us try to look it further. And so if we substitute mx double dot plus kx is equal to f naught e to the power I omega t, what we get is this xp bar, right, xp bar e to the power I omega t plus k into x. So, xp bar o e to the power I omega t is equal to f naught e to the power I omega t, right. So, you can see from here the xp e to the power I omega t naught cancels out, and then we are left with xp bar o bar is equal to f naught upon k minus m omega square, right. And therefore, the solution, the particular solution, the complex solution would be x p o bar e to the power I omega t, which is nothing but f naught upon k minus m omega square e to the power I omega t. But then this is the complex response to the complex exponential force, but our interest was to find the response to the force f naught cos omega t, and therefore, now we take the real part of this response. So, therefore, the true particular solution, which is xpt, is nothing but the real part of this complex force, right, and hence it becomes f naught upon k minus m omega square cos omega t, and we see that it matches with the expression we got for the particular part of the solution using the direct method, right. And hence therefore, this shows that this method works, right, it does give you the correct solution. So, now let us come back to the question that what is the nature of the complete solution, right. So, let us rewrite that expression for the complete solution. X of t was a cos omega n t plus b sin omega n t plus x static upon 1 minus omega upon omega n square cos omega t. So, we note that now there are two parts of the solution, right. This part is the complementary part, right, and it occurs at the natural frequency of the system, right, and this part is the particular part and it occurs at the frequency of excitation, right, occurs at frequency of external force, right. So, of course, let me write here it is complementary part. So, that is I think the one important observation here, right. So, it consists of two parts, complementary part, particular part. Complementary part occurs at natural frequency of system, the particular part occurs at the frequency of the external force, right. And so, this part is as we will see later, complementary part is also referred as transient part, because if damping is incorporated, as we will see later, this part will have its amplitude decaying with time, and hence this part is also referred as transient part. That we will but however see when we take damping into account. So, this complementary part is also, as I said, also called transient part, right, because it is going to die out because of damping, and this part is the only part that would be left after the transient part has died out. Okay, and hence it is also referred as steady state part. Now, A and B are arbitrary constants, and they are to be found from initial conditions on x, right. So, we need to impose the initial condition on the complete solution x and find A and B from there. So, if at t is equal to 0, if the displacement x of t is equal to x naught and the velocity x dot t is equal to v naught, then we get we can find A and B, and if we substitute into the solution, the final equation would look something like this. Plus x static upon 1 minus omega upon omega n square cos omega t minus cos omega n t. Let us know, because the transient part anyway is going to die out because of the damping, the complementary part is going to die out because of the damping. It is only the steady state part due to the external force that is going to be left. So, let us try to study what is the amplitude of the steady state part of the response. So, let us study the particular part or steady state part of the response. So, if you look at the amplitude of the steady state part, then it is given by x static upon 1 minus omega upon omega n square. So, we see that the XPO is a function of omega, frequency omega of the force. If that changes, the amplitude also changes. So, let us plot the amplitude of the response as a function of frequency. And the curve looks something like this. The curve starts at x static, right. So, if we look the behavior at omega is equal to 0, we see that XPO is equal to x static, because if the frequency of the force is 0, then it is a unidirectional force and produces static deformation or deflection in the system. As omega increases, the response amplitude also increases, XPO increases, and we see that it is more than x static. So, that shows that the dynamic response can be higher than the static response. At omega is equal to omega n, right, at omega is equal to omega n here, at omega n what we see, XPO is tending to infinity, right. Okay, it is infinite in fact. The steady state value of the amplitude will be infinite at omega to omega n, and to understand that why this happens, of course from the formula it is clear that it is infinity, but it does not build to an infinite value instantaneously. This formula tells the steady state value of the response, right, and that is predicted to be infinity. But if we want to see what happens and how the amplitude builds to infinity, then we need to look at the basic equation, right, which in our case the particular part of the response was if I rewrite again here, x static upon 1 minus omega upon omega n square cos omega t minus cos omega n t. This was the particular part of the response, right. The other part is going to decay. So, so what is going to happen now? So let us find out the limit of this when omega becomes equal to omega n, right, xpt. So we need to find out the limit of this when omega tends to omega n, okay. And we see that you know, the numerator and denominator both would become 0, and hence we can use L'Hospital's rule, right. So we take the derivative of cos omega t minus cos omega n t with respect to omega, and then we also take the derivative of the denominator which is 1 minus omega upon omega n square. Of course, we also have x static here. So, and then we therefore we get limit omega tending to omega n. This would be x static differentiation with respect to omega would give me minus t sine omega t, right, divided by minus 2 omega upon omega n square, right. And that simplifies to, now what do I get? So if I take the limit now omega tending to omega n, then I get half, I would get t omega n x static sine omega n t. That is what I get as the limit, right, limit of xpt as omega tends to omega n. So we see that the response amplitude, it builds in proportion to time. As time, you know, progresses, the response also builds, and in the limit when, you know, in the limit when t tends to infinity, when t becomes higher and higher and tends to infinity, the amplitude becomes infinity, and that is what is being shown by this curve here, right, showing that the steady state amplitude becomes infinity. So, so if I try to just roughly sketch it here, then what we have got is the amplitude, you know, starts like this and gradually continuously it keeps on building, right. This is x p t varying with time, okay, it continuously builds and then it reaches to infinity. So therefore this is nothing but referred as the resonance condition. So this condition omega, you know, becoming equal to omega n is referred as resonance condition, where the frequency of the forcing function is equal to the natural frequency of the system. And we see that at resonance the amplitude, this undamped system says that the amplitude becomes infinity, right. But obviously, you know, in practice there will be some amount of damping, and that damping would limit the maximum amplitude that can be reached at resonance, right. Okay. So therefore, but then it does says that at resonance the amplitude can be very high, and that is why resonances needs to be avoided. So I think the another thing we need to also would like to define now is what is called as frequency response function. Okay. The frequency response function is the ratio of response amplitude and force amplitude at frequency omega. Okay. So therefore, and if we represent it by symbol alpha, then at frequency omega, alpha omega is nothing but the ratio of response. So this response is nothing but the steady state response or particular part of the response, right, and therefore this is the particular part of the response. So xpo divided by what is the amplitude of the force. Okay. So, so more formally we can write this as, if we represent x to represent the x of omega, if we use to represent the amplitude of the steady state part, and if f of omega represents the amplitude of the force being applied, then therefore alpha of omega is referred as x of omega upon f of omega. So, for the present case of single degree of freedom undamped system, the frequency response function is xpo in our case is nothing but x static upon 1 minus omega upon omega n square divided by the response amplitude, the force amplitude, which is f naught, right. And because x static is f naught by k, right. So, essentially what we get is 1 by k upon 1 minus omega upon omega n square, correct. So, this is what is nothing but the frequency response function. So, the frequency response function essentially tells us the response of the system or the amplitude of the response amplitude to a force, or rather to a harmonic force of unit amplitude. Okay. It tells you the amplitude of the response to a harmonic force of unit amplitude. So, for the present case we can see that we can also write this as, because xpo in our case was f naught upon k minus m omega square, that is the response the particular part of the response amplitude divided by f naught. So, we also get an equivalent result or equivalent expression for frequency response function as 1 upon k minus m omega square, that also we get, right. If you plot the FRF, so I can plot the magnitude of the FRF here, right, as a function of omega. So, this plot is going to look like this. Okay, and this is nothing but 1 by k, and I can also plot the phase of the FRF, right, the phase of alpha omega is a function of omega. So, of course, this is omega n here, and what we see is that the phase is 0 degree when omega is less than omega n, and it is 180 degree when omega is more than omega n. So, this is nothing but the frequency response function, magnitude and phase. I think we will talk more about frequency response functions when we analyze now damped systems and multi-degree of freedom systems, and we will further talk about the application of frequency response function, right, how we can find response to any harmonic force using frequency response functions. This we will talk later, right. So, in this way I think now we can stop here, and today we can see we have studied analytical model analysis of single degree of freedom and damped systems, where we studied the free and force vibrations of the system, right, and we also defined a concept of frequency response function. So, thank you, we will meet in the next class.